Hi, this is Richard C. I'm a math tutor at Wyzant, and we're going to be covering this problem today submitted by a student. This involves vectors. Vectors are a very important topic. They're used a lot in physics, and I'm not going to be able to cover vectors in depth today. I'm just going to cover this problem. Hopefully you wouldn't, well, typically you wouldn't see a problem like this unless you already had a background information on how to deal with vectors. So what we're going to do is first look at the vector for the airplane, which has a heading of 95 degrees, which means it's making the way to do a heading is you look due north. Here's north, south, east, west, of course. And you look due north, and then you just rotate 95 degrees. So the heading is going to look like this with a 5-degree angle here. It's going to go just beyond 90 over to 95, so that you could think of that as a reference angle, if you like, of 5 degrees. And it's going to have a magnitude of 240. So there's the vector. And so the length or magnitude of that vector is 240. But at the same time that the airplane is traveling at that heading, there's wind blowing, and it's blowing at a heading of 150. So we're going to go to 90, and then we need 60 more to get to 150. So that's going to be 3. Let me just put in a 60-degree angle here. Think of this as a 60-degree angle. And you have a very small vector representing wind. But that's a 60 there. A little hard to read. I'm sorry about that. And it has a magnitude of 15. So we'll call this one U. We always, whenever we represent a vector with a letter, and we'll call this V. U and V are traditional choices. So we can say that U, it has a magnitude of 240, and in the x direction, we have a cosine of 355, and sine of 355. This is called the component form of the vector, because it's 355 because all the way around would be 360, and then you're coming back down 5. And then vector V, it has a magnitude of 15, and it's going to be cosine of 300, sine of 300. And that's the component form of vector V. You might be wondering where the component form comes from, and it's really just coming from SOHCAHTOA, believe it or not. So if you had if you just think about this, think about the vector for the airplane. This is 240 here. And if you wanted the x and y distances here, y and x, you would just get them with SOHCAHTOA. X would be cosine of 355 times 240. So if you're wondering, again, I'm not going to get into this in depth, but if you're wondering where these numbers come from, that's where they come from. So now the rest of this is really just calculator work. I'm just going to simplify U, distribute that 240, and on my calculator I get 239.1, comma, negative 20.9. 0.9. So I'm just distributing 240 times the cosine of 355, 240 times the sine of 355. And for V, I'm going to do the same thing. This is going to be, the coordinates of V are going to be 15 times the cosine of 300, which is 7.5, comma, negative 13. If you look at the diagram, these numbers make sense. Think of this as 7.5, comma, negative 13 as the coordinates here of this endpoint. And the endpoint U would have coordinates 239, roughly minus 21, something like that. Now, what I want you to try to imagine is what the resultant, we call it the resultant, would be in this situation. Where would you expect it to turn out to be? Well, because the wind is blowing in the same general direction as the plane is traveling, you would expect the length or the speed of the plane to increase somewhat. And because the wind is blowing more southerly, you would expect this negative 22 here, negative 21 rather, you would expect that to be pulled down. So you would expect the direction would be a little more southerly, and you would expect the speed or magnitude or length of the resultant vector to be somewhat larger. So we're going to find that now. So we're going to go U plus V, and you just go on your calculator and add these two x values together, and you get 246.6, comma, negative 33.9. This is all just from the calculator, just adding these two things together. So that's 239 plus 7.5, and then negative 20.9 and negative 13. So if we wanted to put in the coordinates, we could. So this would be 246 roughly, negative 34. And you could see it's exactly what we expected. It's going to be a little bit longer. You could see it's extended a little bit beyond that 239, which is the x value here. And it's more southerly. It's moving down more toward the direction of where the wind was pulling it. But the wind is not very strong. It's only 15 miles an hour. So we're not going to expect a big deviation from the original heading. And we don't get one. Now, the actual velocity of the airplane is just the magnitude. Again, I'm using some notation that might not be familiar to you. But it's really just Pythagorean theorem here to get the magnitude. It's going to be the square root of 246.6 squared plus negative 33.9 squared. I don't know why that happened. Excuse me. Let me see if I can just push everything to pull everything back here. Here's the problem. I can't seem to pull this back. Oh, darn. Okay. Yeah, I can't seem to pull this back. So just increase the width of your window, and then you should be fine. I'm just about done here. So this turns out to be 248. Excuse me. 248.9. So the magnitude here is 248.9. I'll say it 249. And that makes perfect sense. You can see this is traveling a little bit faster, just a teeny bit faster than the original speed, the speed that they were traveling at. You could think of this as the traveling without a wind. This is the speed that they would be traveling. With the wind, they're traveling slightly more. And because of the wind being southerly, more or less southerly, it's pulling the direction down, so the y is going to be further down. The x value of the resultant is roughly the same. So the direction that the easterly direction is going to be about the same. So that's it for this one. Sorry about the technical problem, but I think you can see what's going on here. So this is usually a fairly early problem in vectors, and you'll be doing more work on vectors, but you can see why vectors are so important. They're used a tremendous amount in navigation and physics. So enjoy the rest of your travels through vectors, and I'll talk to you again soon.